Welcome to this part on Symmetric concerning the syntax and semantics of symmetric nets. So till this point you have got some hints on colored Petri net and in particular on symmetric net, and we go through the precise syntax and semantic of symmetric nets. Okay, but before getting deeper, we have just to recall some small notions that we have to use in the whole presentation next. Okay, this notion is the notion of multisets and or bags, as the two are used. So the notion of multiset is based on the definition of a set. First we define, let's have a set, a non-empty finite set, and on this set here, the set A, big A, we will define the notion of multiset. The notion of multiset small a as a function that gives for each element of a natural number a x, and this natural number is called the occurrence of the element x in the multiset. Okay, and the usual notation of this multiset is as written down here, with the summation of x belonging to big A, while we precede the x by its occurrence here. Okay, so the whole number, the whole multiset that we can handle are noted here by bag of A. Okay, and with this notion we can compose functions for which the domain are bags here. For example, the function f, g, and h all have domains and codomains which are bags. We can compose them, or we can make a Cartesian product from this bags from this function in natural way. Then, for example, for here in the Cartesian product between f and g gives us a new function that operates on bag of C1 cross bag of C1 prime, and the codomain is bag of C2 cross bag of C2 prime. So this is very useful when we'll treat later on some linear functions on the symmetric nets. Also, we can compose those functions in a natural way to obtain more complicated functions that operate on bags. Okay, with this notion of bag, now we can go through the definition, the formal definition of symmetric net. Here I will present some definition which is simpler than the real one, to simplify just the comprehension of the concepts. So, as usual, the definition of symmetric nets are a tuple composed of the traditional place and transition nets with place and transition sets with the traditional constraints here between the place and the transition, like the intersection between the place and transition are empty, and the union between the transition and transition is not empty. What we have more to define here is the notion of the class or color domains. Okay, we will associate to each place and to each transition a color domain. Okay, and if I make a parallel with programming language, it's like you make a type for each variable and a type for each function. It's the same notion we can get here. And what we can stress here is that the modeler has to put for each place its domain. Okay, it's the type of its place, but the domain of the transition are automatically computed from the connected places, as we will see in a second. Okay, so also we have this two things defined here, which are the backward and forward incidence matrix, like we have in ordinary Petri net, but here they are more complicated because they treat bags. Actually, the backward and forward incident matrix are metrics indexed by place and transition, as you can see here, and the place and transition for each entry of this matrix, of these matrices, the function is linear. Okay, so for example, for the entry PT here, for the entry PT, we define a color function which is a linear function that takes a domain CT and codomain bag of C of P. Okay, so I have to stress this point because the whole thing is based on the fact that the function that we will manipulate here are linear functions. Okay. Also, we have two other points to cite here, which are the, of course, the initial marking, which is simple vector indexed by places, and for each place, each entry indexed by P has as the main bag of this color domain of P. Okay. Also, we have this notion of guards. So each transition can be guarded. It's not an obligation, but well, you can. It's in the syntax. You can use it. Each transition can be guarded by a function or a predicate. Here, I treated it as a function from the domain of CT to the Boolean domain. It's something which is very useful when you try to model problems, distributed problems, and to have some constraints on the transition to enable them. Okay, we will see some example on that later on. The final thing that I have to treat here is on the Cartesian product associated to the places. So each place has its own domain. Usually it's a simple domain. It's a simple Corel class, what we call a Corel class, a type, a finite set of elements, but we can manipulate also Cartesian product of simple domains or simple classes. Okay, but that's all what we have in symmetrical net. We don't have more complicated, let's say, structures like I don't know, heaps and lists. We don't have that. We have only simple domains or Cartesian product of simple domains. Okay. For the semantics of the well-formed net, or sorry, here called symmetric nets, they are based on three traditional notions, which are the notion of marking here, the notion of enabling, and the notion of firing, which defines the whole semantics of the net. Okay, the notion of marking, as I mentioned in the previous slide, is simply a vector indexed by P, and each entry of this vector, is a bag of the domain of the entry. Okay, here, for example, if you take the entry P, its contained is the bag of the domain of P. Okay, this is the first point. And if we want to treat the enabling of a transition, the enabling of a transition in the sense that it can be executed or it can be used. So in this case, we have to ensure two conditions. The first one here is that the fact that the guard associated to the transition must evaluate to true. Okay, if any. In many cases we haven't a guard, but if there is a guard, it must evaluate to true for the considered here color to be fired and to be used. Okay, CT. And the second point to ensure here is that expression here, that inequality here, which says that the marking of a place P must be greater than the bag associated to the entry here PT for the color CT. I remember that the pre-function or the for a backward incidence matrix here W minus is a matrix indexed by B and T, and for each entry here PT you have a bag on the transition color domain CT. This is for what we have this somehow complex inequality here. This, if we guarantee this 2 point, we are sure that the transition is enabled for the color CT. Okay, if it is enabled, then we can file it, we can execute it. If we execute it, we have just to compute the successor, the marking reached from this point, and the marking reached from this point is obtained by applying this function, this formula here. Okay, so for each place P, the successor or the next marking of this place P, what we here I noted by M prime of P, is computed from the actual marking of P and P, and from which we retrieve a set or the bag of tokens, the bag of tokens indicated by the backward incidence matrix for the color CT, and we put, this is the, because we have a minus here, and we put the set of tokens that are indicated by the entry PT with the color, with respect to the color CT. Okay, and this is the whole formula to apply to get the successor marking. The remain point is just a notational point that says that if we are in marking M, then the successor marking is M prime using the transition T for the color CT. We have always to associate these three notions to get the successor relation. Okay? Let's go now through a small example that will illustrate all the concept that I mentioned till now. And the concept is very simple. The example is very simple. Here we have three places, as you can see here. The three places called P1, P2, and P3. And the three places are associated to color domains, the two domains here. And for example, the place P1 is associated to the color domain that I called here C1. Okay, it's type. The place P2 is associated to the class or to the color domain C2 here. And the color domain of P3 is here the Cartesian product. I talked about that. The Cartesian product between the classes C1 and C2, which are non-empty finite classes. Okay, and now the color domain of the transition T is automatically deduced from the connected places. Okay, there is more complicated formula to apply, but well, in fact, at the end, it's that. Okay, so the color domain of the place T is the Cartesian product of C1, C2, because the domains that appears in the connected places, the three connected places, are only C1 and C2. Okay, and that's the whole thing. What remains here is that the definition of the color functions here that you can see here. The color functions here, I defined them in that way here. X of I, for example, if we take the color function x1, it's a color function that has as domain the one of T here, C1 cross C2, and the codomain of this function is C. For the x1, for example, it's C1. Okay, I just factorized the representation and makes it xi. But actually, if we take the x1 function, it's C1 cross C2 to C1. Okay, and it's simply a projection function. Okay, it takes a color here, for example, C1, C2 for the function x1, and returns the color x1. Okay, C1 for here, and if you take the color x2, if we take the color function x2, so its definition is the same, C1 cross C2 to C2, and its formal definition is just x2 for x C1 C2, and returns C2 as a result. Okay, so now if we try to see if the color here C1 C2 is enabled, actually we have to ensure that the two conditions hold, the condition on the guards holds and the condition on the equality holds. And here, since we have no guards, so automatically it holds. And the second point is to see if the inequality holds here for this color here. And in fact, it is the case, because here what is described by the function x1 is the fact that we need to fire the color C1, C2, we need at least one color C1 in the place P1, which is defined here. as you can see here. Okay, and we need one color. And in fact, this is the case because you can see here that in the place P1 we have already one color C1. Okay, and for the second function defined on the arc between P2 and T, we have this second the second inequality holds also because we have already one token C2 in the place P2. So the whole token C1, C2 is enabled in this transition and can be fired, okay, can be executed. And when we fire it, the associated output function here, which is the Cartesian product between C1, X1 and X2, produces actually the tuple C1, C2 in the place P3. Okay, that's the whole thing according to this example. So let's go through the same example, but a little bit more complicated. So here I defined two color classes, C1 with 3 elements, A, B, C, and I defined in the C2 as a set with alpha and beta. Okay, and I started from this marking here, where I have in the place P1 two colors, A and C, from the domain of P1, which is here C1, and I marked P2 with alpha, since alpha is an element of the C2, okay, and I marked the place P3, okay, and I apply I marked P3 with the color the color C beta, since the color domain of P3 is C1 cross C2. So I can use one element from each color class. Okay, and I want from this starting marking to go through a firing of a certain instance. And here I can observe that the transition T here can be fired, as you can easily see, with this instance A alpha. Okay, because if we instantiate each element of the Cartesian product by an element, we can instantiate C1 with the element of C1 by A and by the element of C2 by alpha, and we can see easily that this instance is enabled since we have the preconditions that are already satisfied. We have alpha A in the place P1 here, we have alpha in the place P2, so we can fire with this transition, and the obtained marking will be the move of alpha, of A alpha in the place P3, as you can see here. And this transforms this marking here to this successor marking here. Okay, and this is the whole thing that we can speak about the firings. Okay, so the remaining point that we have to discuss here is the point concerning the basic function that we allow. Okay, we said at the beginning that in the formal syntax we authorize only linear functions. Okay, only linear functions on the color on the arc, so on the color functions. Okay, and we don't allow any linear functions because we have only 3 functions that we manipulate. The 3 functions that we cite here immediately here are the identity, okay, function, the successor function. When you have a certain notion of order on the classes, because we, as you can see in the examples later on, that we have to manipulate order classes and unordered classes. The unordered classes, what we have seen till now, and the order class we associate to the class notion of order of in the enumeration of the definition of the class. Okay, so we can associate to that class's function called successor, so to obtain the successor color. And the third function that we manipulate is the diffusion, which is a constant function actually. Okay, a constant function. So these 3 functions, I just described the informal point here. These 3 functions can be combined linearly and we can obtain a big amount of facility here to describe the models. Okay, so here, to be precise, here we can on color domain, what we can have is a Cartesian product of classes, and we can repeat any class anytime you want. Okay, any number of time you want here, as you can see in this expression here. So a color here from C can be of this form. So you can, for example, make C1 cross C1 cross C2, okay, or C1 cross C2 cross C1. This is allowed also. So in this case, you will have some tokens from the form of small c1, small c2, and small c1, if it is c1 cross c2 cross c1, okay? And in for these colors, you can manipulate them with these three functions here. For the identity, we'll take the projection on the needed class. For example, if you have the color domain c1 cross c2 cross c1, and you want to extract the first element of the tuple, you have just to write something equivalent to x of 1, 1 to extract the first element. To extract the second element, you have to write x1 of the second element, and so on. Okay, the same holds for the successor relation, for the successor function, while the additional point is just you have this successor or this ordering that comes in front. Okay, and the third point here is the diffusion, where it's a constant function. It doesn't depend on the parameter c. And what it mentioned is that we have to take the whole to be satisfied. We have to take the whole element that belongs to the color of a place to be satisfied. So what you have to keep in mind here is that the function that we manipulate in in symmetric nets are linear combination of these three functions and nothing else. Okay. Until to end my part here, I will do just a small sum up. So until this point, you have a small idea on the syntax and semantics of symmetric nets, the enabling condition, and the firing rule. So here we will go deeper on some small examples given by